Notice that I'm sharing my screen. I just have a couple, a couple things that I wanted to make sure that I didn't forget. So we're switching back to our small groups in lab this week. We will meet in S257 at, when I say our normal time, so either 8 a.m. or 9 a.m. We're going to be, you're going to have a chance to look at some powder metallurgy parts, machining parts, and then plastic parts. So again, we'll have some time and we'll be doing surface roughness on some machine parts, actually the design of experiments, and we'll talk a little bit about what a 3-factorial design of experiments is. So we'll be working with surface roughness on the milled surface that we did calculations on. Okay. My anticipation also is that I will have the machining homework. I anticipate that I will print that and grade it and have that to be returned. That's as much for you guys to remind me to do it, because I forgot with one section on the exam. You also may have noticed that there are 2 more reading assignments posted. Both of those are due next week. One is on joining and one is on additive manufacturing, and then that will be, that's the end of the reading assignments. And then I got lulled into thinking we were somewhat back to normal, because I've had all of you in the Harley Lab, or S130, and it occurred to me that our final presentations, we need to kind of think about like how we want to run those. I believe on Thursday of week 10, S206 is available. So it's possible that we could so we have a couple options, and I just want you to kind of think about it. I need to think about it as well in terms of logistically what makes sense. I can try to get a room for that week, probably Thursday, Friday. And that way all of us could be in person at our presentations, or I could maybe get a room for one day, or we could do what we've been doing where there's in person and then presentations, and then some of you are online. One aspect that I believe I mentioned, but I want to kind of say it again. For 323, the final is going to be different than most finals, in that there will be sections and students can choose which questions in a section that they will answer. So for instance, there'd be a casting section and you would answer 5 out of 8 questions or something along those lines. I also have a small section, maybe 10 to 12 points with 2-point questions that come from the student presentations. And so I think in the handout, I did say that I want for every presentation for you to have, make a paragraph or 2 abstract that you would make available to your fellow students. And then the very last homework assignment is for every student during the presentation to write down one potential finals question for the final. So we do need to make sure that we're aware that there will be questions on the final from the presentations. And again, it will be some of that. You can choose which ones you answer. So we need to kind of think about it. I don't want to make any decision now, but start kind of bouncing around in your mind if you want to do online presentations or in person, all in person. I'm kind of, I haven't decided what works out the best on that. Okay, so with that, if there are questions, now would be great. If not, we will move back into talking about plastic processing. Okay. Okay. I have yet to figure out why sometimes this decides to work and sometimes it does not. Okay, so on Friday, we did start talking about rotational molding, and our additional processes will be blow molding, thermoforming, and rotational molding. So we're going to do rotational molding instead of the last process, the first of the additional processes. And again, I always think it's kind of nice to have some some examples of rotational molded parts, and then these are some, and I do have a short video clip that we'll look at as well to see the process. Now, rotational molding sometimes is also called rotomolding, and so we have a closed mold, and we place the polymer, and the polymer is going to be for rotational molding, it's not that granular. That would be very unusual. It's going to be in a powder or a liquid form, and it really just depends on what material we're looking at. It's going to be poured into a mold that is closed. So there'll be a little opening at the top. We pour the polymer in, and then it's heated and rotated. So, we kind of put the material into a mold, and then it's rotating on multiple axes and heating. So as the material falls against the hot mold, it's going to fuse. If it's a thermoset, we're going to have that chemical reaction. If it's a thermoplastic, we're going to have those molecules or chains kind of move relative to each other. So the material is going to hit the hot surface, it's going to fuse, become a solid part, all the while it's rotating. The mold continues to be rotated as it's cooled, and then once it's cooled, the mold is opened and the part is removed. So it's, if you're kind of thinking, there's not a lot of pressure. It's not really that complicated or expensive of equipment, and we're going to see that indeed is the case. Kind of a fun note, hollow chocolate balls was one of the first processes or one of the first products that was made using kind of the early rotational molding. So, and I suspect that, some others were as well, but certainly those hollow chocolate balls. Okay, so here is an example of a rotational molding part. So you can kind of see, here's the mold, and we kind of have the rotational aspect, what rotates right here. Okay, so I think this is probably a good place to stop and look at our rotational molding. So this particular video is by the company that makes the rotational molding machines. Listen for things like cost, variability, and there's one particular aspect of this process that's never mentioned, and we'll talk about that as well. Okay, so here we go with our video, which hopefully you can see and hear.
Consider the possibilities. Tough, lightweight, one-piece plastic products. Almost any size, any shape, any color. Practical, rust-proof, affordable. There are markets for products like these. Emerging markets, established markets, profitable markets. A world of markets. Hold-in tanks, toys, housings, outdoor furniture, components. And all these products have one thing in common. They are all rotationally molded. Rotational molding is a three-step no-pressure molding process. Step 1. Plastic resin is loaded into the enclosed mold, which moves into an oven station. Here, it's heated and slowly rotated in two planes. Biaxial rotation, melting the resin, and spreading an even coating over the inside of the mold. Step 2. The mold, still rotating, moves into a cooling station. Step 3. The mold, now cooled, moves to a servicing station where the part is removed and the mold recharged, ready to begin another cycle. Consider the possibilities. High or low volume, fast turnaround, a variety of materials, complex shapes and different textures, graphics and inserts molded right in, less lead time and lower mold costs than any other polymer molding process. Now, consider that Ferry Industries is setting world standards for rotomolding excellence. Quality, technology, reliability, and support. 6 machine styles, 30 models. Complex machines made simple. Each one custom configured to get you where you want to go in the rotomolding business. Ferry makes the largest production machines in the world. And Ferry pioneered the modular 5-station independent arm machine, the ultimate in molding flexibility. Multiple products on the same machine at the same time. There are also 3- and 4-arm fixed turret machines for long run and other product applications, semi or fully robotic. Rocking oven machines for long, narrow products like canoes and lampposts. Express shuttle machines.
Okay, I did want to take us at least into the to the canoe one, the rocking one. So even though that's not, you know, quite rotating in the same way, that's still your general kind of concept. And so the outdoor furniture still amuses me because I think of a picnic table, not a porta potty. But you kind of get the idea of some of the size scale. You also saw some of those very large tanks, a lot of sport, you know, some sport toys and sporting equipment is also made with rotational molding. The one thing that, so what was mentioned in the video about time? So what was the, because we know that time is one of those characteristics that we care about. What was mentioned in terms of time? Okay, lowest lead time. And yes, so, and lead time is going to be the time between, oh, I have an idea and I can get a part. There's a time that wasn't mentioned that would not be a strong point for this process. What do you think it has a very, so rotational molding does have a short lead time. What time would it be? Would it have long? What would be a long time for this process? And let's say compare it to injection molding. Cycle time. Yes, thank you, Jacob. Yes, and so a lot of times we see that. So rotational molding does have a short lead time, but it also has a long cycle time. you tend to not hear those sort of, I'm not even going to say negative, but they're not going to say, hey, this process has a very long cycle time. It's going to be more on the lead time, which it does have a short lead time and the long cycle time. So let's kind of look again. We're going to go with the characteristics of rotational molding. And I'm going to, let's sort of start with short lead time. And again, this is the time between I have an idea and I can get the part. So the molds themselves, or the tooling, are relatively simple. And again, compared to injection molding, we do though have long cycle times. Even explaining it takes a while. And that's because we're rotating the part while it's being heated and cooled. We have low tooling costs, which is nice. Again, the tooling is relatively, relatively simple, again, compared to the molds for injection molding. We also have low equipment costs. It can look fairly complicated, but it's really on the simple size. Very, very large parts possible. And let's see if I have that. And so kind of here, and so we can kind of look at, the large tanks, canoe, playground playground equipment, and so forth. We can do insert molding, which they showed, and some thermoplastics and some thermosets possible. So not every plastic can be rotational molded, but there are quite a few that can. Okay. Now, if we consider the parts themselves, and so, the first thing is we sort of look at the process, and that's going to kind of give us an idea of, what's in a suitable quantity, what materials, but what about the parts themselves? And so if we go back to residual stresses, there is not a pressure gradient, and any temperature gradient you have is very, very small. So there's no residual stresses. And again, that can be helpful for certain products, especially tanks that are going to hold any sort of chemical. Now, the wall thickness, so we have thicker walls than other processes. This really is, in some ways it might be a negative, in some ways it's a positive, in some ways it's a neutral, in that we cannot get really thin sections, but if we want a thicker wall, this is a really good process for that. Now, the dimensional tolerance is not great. Also notice that tolerance wasn't talked about. They talked about texture, they talked about insert molding, they talked about complex shapes, but not dimensional tolerances. So dimensional tolerances for rotational molding are, of the 4 processes that we're looking at, these are going to need to be the largest. So you really can't get fine dimensional control. We again can have different textures, basically like just by what's inside the mold. And again, rocking molds can produce long parts. And again, that's the canoes and kayaks. Okay, so I'm going to also just kind of put a note here. The low tooling costs, when I say make, allow for low quantity. Yeah, so again, we kind of often see that the processes that have low tooling costs often we can do a small quantity, but we may, there are things that I don't want to say suffer in the end. Oh, okay. Let me just, I have a particular, okay. Let me just, I have something that I wanted to put with this. Okay. Okay, so this is the part that we saw in the beginning, and I said that this one is a little bit smaller. This is a part that we will have available to look at tomorrow and Thursday in class or in the lab. So here is, it's what would be considered a calibration foot for an MRI machine. So it has the reasonable, it's a semi shape of a foot. It could be filled with different substances. It would be used again to for calibration on both what you could see in the MRI and what you cannot see in the MRI. So it's a very, very low volume part though. And so injection molding was not really a good option just because of the quantity. However, it is an example of a part where you need to have very good dimensions. So rotational molding did not have the dimensions needed. And so one of the compromise was to make it out of rotational molding, make it larger, and then it would be machined into the proper shape and size. More on that. So again, I thought this was a good example of where you couldn't get the dimensions, but one of the things that we can do oftentimes is make it larger and then machine into what we want and need. Okay, so that is our quick look at dimensional, at rotational molding. And let's go back to our processes and move on to blow molding. Okay, so the other process that we can talk about, and oftentimes there are competing processes, and so many parts can be made by multiple processes, and the question is, which process is the best for this particular situation? If you're thinking, oh, blow molding, it's in some ways we might say it has some similarities with glass blowing. It is very good at making containers in some sort, and sometimes we can be very creative and expand sort of the definition of containers. Now, you may be thinking, oh, that's like that, that's that traffic cone or traffic barrel. I saw that in rotational molding. There is a fair amount of overlap between these two processes. A lot of our consumer products, water bottles, soda bottles, you know, the containers that have sort of, you know, our detergents, our milk. Here we have, again, some of these are hollow, some are not, our double-walled tool chests, and then some of our containers as well. Approximately 95 gallons is about the high side for blow molding, and that is on the like middle to low middle side for rotational molding, but there is a fair amount of overlap. Okay, so now blow molding we could sort of consider to be like kind of a two-step process. And the basic process is we start with something that we call a parison. It's basically a preform. Depending on which process we look at, whether it's injection molding or extrusion, the parison's going to look a little bit different. I'm going to just kind of go ahead a little bit and look at a parison or the preform for a bottle. This was made by injection molding. We can actually see the little gate up here, and the screw threads for the cap are injection molded in, and then we have the material that will be expanded to form the bottle. Okay, so we start with this preform, and that can be made either by extrusion or injection molding. The parison is going to be warm. It's placed into the blow mold, so it's placed into the mold that is split, that has the outside, the shape of the outside. Then hot air is injection into the parison that forces it against the hot mold cavity. So we have the hot thermoplastic against the hot mold. The mold opens and the part is removed. Now, this is limited to thermoplastics. However, we can have multi-layered thermoplastics. So, and I believe I have an example of a multi-layered thermoplastic, not for blow molding, it was another process, but we can have different layers, which allows us to, especially for tanks, customize our product. Okay, so for extrusion blow molding, and extrusion blow molding is commonly used for a lot of your like milk jugs and laundry jugs, and it can be used for other processes as well. Again, we have our extruder. So here's our reciprocating screw that's going to sort of push the material through a die. It's going to kind of go into making just sort of a thin sheet of material. It's going to, the mold cavity is going to close. Hot air is going to expand it against the mold. Then the mold will open and we have the part. I do have a quick video clip of blow molding as well. Here is a picture of parts that were made by extrusion blow molding. You oftentimes sort of can see the flash at the parting line. Injection blow molding, we actually injection mold the parison or the preform. We put it into the mold. The air, we oftentimes have something called a core rod, so that's going to deliver the air, and it encourages or it forces the material in the parison against the mold. Then the mold opens and we have our finished product. Again, our injection molded parison oftentimes has the screw threads for the cap nicely there, and you can sort of see how it has become the bottle on here. Okay, I think this is a good time to, again, show my, why is this? There we go. Okay. No, I don't want this. Okay. I thought I could have both out. Where's my, here we go. Here we go.
Blow molding processes are the most popular methods used to produce hollow products out of thermoplastic materials. Blow molding evolved from the ancient art of glass blowing. Today, it is a leading plastic manufacturing process because of the wide range of plastic resins that can be blow molded and the many possible methods of blow molding. Blow molded parts range in size from the very small to extremely large parts. Bottles and containers are the most common blow molded products, but other items such as highway barrels, automotive components, double-walled cases, toys, medical items, and structural panels are produced. Blow molded products are formed from thermoplastic resins such as high-density polyethylene, medium and low-density polyethylene, polyethylene terephthalate, polypropylene, polyvinyl chloride, thermoplastic elastomers, polystyrene, polycarbonate, fluoropolymers, polyimide, and many other materials. Most thermoplastic blow molded products are produced via extrusion blow molding using high-density polyethylene or HDPE. But there are many additional blow molding processes which include injection blow molding, biaxial stretch blow molding, and co-extrusion blow molding. These blow molding processes all use elements of either extrusion or injection molding or a combination of the two. In addition, these blow molding processes all share four common stages: plasticizing or melting the resin, Parison production when referring to most blow molding operations, or preform production when referring to biaxial stretch blow molding. Parison or preform inflation and cooling in the blow mold, and ejection from the blow mold. A fifth stage is necessary in extrusion blow molding for trimming and finishing the product. For the most part, blow molding processes all use the same blowing technique, whether it be through a blow pin, a needle, a stuffer, or core rod. It is in the production of the parison, or the preform, where these processes differ. The process of extrusion blow molding involves applying heat and pressure to thermoplastic resin to produce what is called the melt. This melt is then forced through a die to produce a parison, which is then dropped, trapped, or conveyed to an open blow mold for subsequent blow molding. Extrusion blow molding uses either an intermittent or continuous method for the formation of the molten parison. Intermittent extrusion produces a parison only when the blow mold is ready. These parisons are produced by using either a reciprocating screw or an accumulator and ram style machine. Injection blow molding incorporates elements of conventional thermoplastic injection molding with blow molding and is generally more economical than extrusion blow molding for containers under a quarter-liter in size and large production runs. Injection blow molding machines typically contain three stations: the injection station, the blow station, and the strip or eject station. The injection station is basically an injection molding machine. A ram, usually a reciprocating screw, forces the melted thermoplastic resin under pressure onto a metal core rod held within a closed split parison cavity injection mold.
After the outside skin of the parison has set, the parison mold opens, and the core rod carrying the parison rotates to the blow station. Once the core rod is in position, the blow mold closes. A trigger bar opens the core rod air passage. The air lifts the parison from the core rod, except where it is held at the neck, and expands it to the shape defined by the blow mold cavity. Once the part has cooled sufficiently, the blow mold opens and the part is indexed to the next station for stripping or ejection.
Okay, so that is, blow molding. It is the injection blow molding. You can kind of see, if you notice, that was a 3-plate mold, so the gating system was not removed with the part. So kind of interesting. I always kind of think about extrusion blow molding, that the parison coming down, I always think is kind of fascinating. So again, while this is not a blow molded part, it is an example of a multi-layered material that we could blow mold. And we see that we've got some different kinds of materials that are all, and there's one inside as well. So multiple layers where we've got some fibers, but also some other plastics as well. So one of the things about thermoplastics is that they very easily adhere to each other, and we can make easily multi-layered parts, which then we can blow mold into shapes that we're interested in. Okay, so let's look at some, again, characteristics of the process. Okay. So overall, we have lower mold costs. So again, this would be tooling. And this is going to be then injection molding. So injection molding, we sort of compare everything to. Minimal residual stresses. So we don't see a lot of, injection molding tends to have high residual stresses. It is very good for hollow shaped parts. And that is also going to do like double walled cases as well. And so if you remember from the video, they were pulling off some of the double walled cases. And we also can do single or multiple layered parts. And especially with our multi-layers, can be made with extrusion blow molding. Now, one of the things that I think is kind of interesting about blow molding and this concept that we can do multi-layered parts and we get minimal residual stresses is this idea of containers or tanks. And one of the things that we might not think that much about, but fuel tanks, especially fuel tanks on automobiles. Now, I'm as old as dirt compared to you, but when I was growing up, plastics were not used as much in automobiles as they are today. And fuel tanks, or your gas tank, was pretty much made out of generally made out of metal, and you had very limited shapes. So trying to figure out where to put the fuel tank was an interesting design challenge because it pretty much needed to be like a box-like shape. We also kind of realized that for fuel, we need the outside of the tank, especially that which should not have any contact with the ground, but it needs to be very abrasion resistant, where the inside of the tank needs to have like better, let's call it environmental or corrosion resistance. And so those are going to be different materials. So one of the things about a multi-layered part or a tank where we could have the inside of the tank be one that is very chemically stable, it doesn't react to the fuel, it's going to not contaminate the fuel. We could have a layer that kind of gives us some maybe strength and toughness, and then we could have an outside that could be very abrasion resistant. And so that's kind of exciting. Also, the shape flexibility you have with blow molding compared to sheet metal also allows car designers to kind of look at the space that's available and design the shape of the gas tank to more fit the shape that's available. So I always thought that was kind of fascinating. Okay, so now let's look at some features of blow molded parts. Now, the detail we get is not as sharp as injection molding. So if we want really fine detail and dimensional tolerances, injection molding is going to be will be better. And again, our dimensional tolerance is not as good as injection molding. Usually not uniform wall thickness. This can be an issue. It's not always. And just note, 95-gallon trash can is approximately the upper limit. Again, very good process for the right shape and material. Okay, well, let's finish off, and I don't have a video to go with this process, but we did talk about it a little more in our textbook, and that is going to be thermoforming. So thermoforming, again, these parts were all made by thermoforming. Some of the shapes are shapes that we could make by other processes as well, especially injection molding. Now, our thermoforming process is we basically take a sheet. So thermoforming, we start with a plastic sheet. So we have our plastic sheet, and we are going to take our sheet and heat it above. So we are going to take our plastic sheet, we're going to heat it, and we're going to force it against the mold. So it's a really basic process where we, again, heat our plastic sheet, force against a mold, cool, and remove. Okay, so we're heating it above the glass transition temperature, but below the softening temperature. And we can force using either mechanical means or vacuum. So sometimes we refer to this as vacuum forming. That's the same thing as a thermoforming. We have both positive and negative forming. So if we're doing a positive forming, we're forming it over the mold. So here, this would be a positive thermoforming. So our plastic sheet. So in positive thermoforming, we basically define the inside of the part. Negative thermoforming, we're forming it into the mold. And so here we're going to sort of define the outside of our part. Cool, demold, and edge trim, because we do end up with extra material. So thermoforming is very similar to kind of a sheet metal process. Definitely we need thermoplastics for this particular process. What we realize is we do have higher material costs because we have the plastic sheet. We do generate scrap because we have trimming. Not all thermoplastics can be easily thermoformed. So we do have some, there's more material limitations. We have limited part shapes. And we only are defining one side. However, we have low tooling and equipment costs. And fairly fast cycle times. However, larger part thickness will increase. So if we have a thicker part, it's not always going to be quite as fast. Okay. So some of the features of thermoformed parts, again, only one side is defined by the mold. And that's either going to be sort of the inside or the outside, depending on if it's positive or negative. Some residual stresses exist because there is going to be a pressure gradient. There will be some wall thickness variation. Large parts are not an issue. And interestingly enough, we can make hollow parts in what we call a twin sheet thermoforming. So for thermoforming, if you kind of think about what are some parts that really are well suited to thermoforming, again, anything where we really just are defining the sheet, truck liners, refrigerator linings. If you've seen some of those commercials for the tub enclosures, a lot of those are going to be thermoformed. We can also get some similar shapes. The container on the left, this could also easily be made by thermoforming. Sort of this container, I wouldn't say container, but yeah, it is a container on the right, happened to be thermoformed. It also could have been made by injection molding. And then we can look for some of those telltale signs that a product has been made one with the other. Thermoforming is has some very good uses. It also is a process where, because you're taking the sheet, you're heating it and you're forming it against a mold, it's probably the process that you can, you could actually, we've had students kind of make their own kind of thermoforming device with a heat lamp, in a relatively easy arrangement. Okay, I have that it is 9:50, and so it's time for us